Welcome to an extraordinary journey into one of the universe's most fascinating phenomena. Picture this, a star more massive than our sun, yet compressed to the size of a single city, spinning at mind-boggling speeds of hundreds of rotations per second. From its poles, intense beams of radiation shoot out into space like cosmic lighthouses, so powerful we can detect them thousands of light years away. These remarkable objects are called pulsars, and today we're diving deep into their extraordinary physics. The sheer scale of a pulsar's density challenges human comprehension. Consider this astonishing fact. A single teaspoon of pulsar matter would weigh more than all Earth's buildings combined. This isn't science fiction, it's the reality of these incredible cosmic objects. When you hold a teaspoon of sugar, you're holding about 4 grams. Now imagine that same volume containing more mass than every skyscraper, house, and structure on our planet. This extreme density makes pulsars unique in our universe, offering us windows into physics we simply cannot study anywhere else. These cosmic laboratories are irreplaceable in our quest to understand the fundamental laws of nature. On Earth, our most advanced facilities can only scratch the surface of the extreme conditions that exist naturally within pulsars. No human-made experiment can replicate their intense gravitational fields, powerful magnetic forces, or the bizarre quantum effects that occur in their ultra-dense cores. Every observation of a pulsar is like conducting an experiment under conditions that would be impossible to create in any laboratory on Earth. As we embark on this exploration of pulsar physics, we're not just learning about distant celestial objects, we're uncovering the very foundations of matter, energy, and the forces that shape our universe. From Einstein's relativity to quantum mechanics, pulsars put our most advanced theories to the test, sometimes confirming our understanding and occasionally challenging it in unexpected ways. Before we delve deeper into the fascinating world of pulsars, I encourage you to join our community of cosmic explorers at Exploring the Universe. By subscribing to our channel, you'll ensure you don't miss any of our upcoming content about the wonders of astronomy. Together, we'll continue to unravel the mysteries of these extraordinary cosmic lighthouses and many other fascinating astronomical phenomena that make our universe such an incredible place to explore. The journey of a massive star towards becoming a pulsar is one of the most dramatic transformations in the universe. When a star with a mass between roughly 8 and 20 times that of our Sun reaches the end of its life, it undergoes a spectacular process that challenges our understanding of physics at its most fundamental level. Let's unravel this fascinating sequence of events that leads to the birth of a pulsar. At the heart of stellar death lies gravitational collapse. When a massive star exhausts its nuclear fuel, it can no longer maintain the delicate balance between gravity pulling inward and radiation pressure pushing outward. This triggers a catastrophic collapse that happens in mere seconds, a blink of an eye in astronomical terms. The star's core, which took millions of years to evolve, suddenly implodes under its own weight. During this collapse, the core's density increases dramatically and temperatures soar to unimaginable levels. The physics becomes even more fascinating when we consider what happens next. As the core compresses, electrons are literally squeezed into protons, forming neutrons through a process called electron capture. This creates an extraordinary state of matter, a neutron-degenerate material. Unlike ordinary matter, this substance is held up not by atomic forces, but by quantum mechanical effects known as neutron degeneracy pressure. This pressure arises from the Pauli exclusion principle, which states that no two neutrons can occupy exactly the same quantum state. One of the most captivating aspects of pulsar formation is the conservation of angular momentum, which leads to the extreme spinning speeds these objects exhibit. This is where our ice skater analogy becomes particularly illuminating. Just as a figure skater spins faster when pulling their arms close to their body, a collapsing star spins faster as it shrinks. However, the scale is almost beyond comprehension. While a star might have been rotating once every few weeks, the resulting pulsar can spin hundreds of times per second. To put this in perspective, imagine our Sun, which rotates approximately once every 27 days at its equator. If it were to collapse to the size of a typical pulsar, roughly 20 kilometers in diameter, while conserving angular momentum, it would spin so fast that its surface would be moving at a significant fraction of the speed of light. This incredible rotation rate is one of the defining characteristics of pulsars and plays a crucial role in generating their distinctive pulsed emissions. The conservation of angular momentum during stellar collapse is a perfect example of how fundamental physics principles that we can observe in everyday life scale up to explain some of the most extreme objects in the universe. The same physical law that makes a spinning office chair speed up when you pull your legs in is responsible for creating cosmic lighthouses that flash with clock-like precision across thousands of light years. This transformation from a massive star to a rapidly spinning pulsar also results in an intense concentration of magnetic field lines. As the star collapses, its magnetic field is compressed along with the stellar material, resulting in field strengths that can be trillions of times stronger than Earth's magnetic field. These incredibly powerful magnetic fields, combined with the rapid rotation, are what enable pulsars to accelerate particles to enormous energies and produce their characteristic beams of radiation. The physics of stellar death and pulsar formation represents one of nature's most extreme laboratories, where we can observe the interplay of gravity, quantum mechanics, and electromagnetic forces under conditions impossible to replicate on Earth. Understanding these processes not only helps us comprehend the life cycles of stars, but also provides crucial insights into the fundamental forces that govern our universe. The matter found within pulsars represents some of the most extreme conditions in the universe, showcasing states of matter that exist nowhere else in nature. In these extraordinary objects, ordinary atomic physics breaks down completely, giving way to an entirely new realm of nuclear and quantum phenomena that challenges our understanding of fundamental physics. Let's begin with the states of matter inside a pulsar. Unlike the familiar states we encounter daily, solid, liquid, gas, and plasma, pulsar matter exists in an entirely different form. As we move from the surface towards the core of a pulsar, we encounter a series of increasingly exotic states. The outer crust consists of a lattice of atomic nuclei immersed in a sea of free electrons, similar to a superdense metal. Deeper inside, the tremendous pressure forces electrons to combine with protons, creating a neutron-rich environment that defies our conventional understanding of matter. Electron degeneracy plays a crucial role in pulsar physics. Under the immense gravitational pressure, electrons are forced into their lowest possible energy states, prevented from occupying the same quantum states by the Pauli exclusion principle. This quantum mechanical effect creates a powerful pressure that temporarily resists gravitational collapse. However, in pulsars, even this isn't enough to prevent further compression, leading to the next extraordinary phase: neutronization. Neutronization represents one of the most remarkable transformations of matter in the universe. Under extreme pressure, electrons are literally squeezed into atomic nuclei, combining with protons to form neutrons through inverse beta decay. This process, occurring at densities around 10^11 grams per cubic centimeter, transforms the star's interior into what is essentially a giant atomic nucleus. The result is a structure where neutrons dominate, creating what physicists call neutron-degenerate matter. The density achieved in pulsar cores is almost beyond comprehension. At the center, matter is compressed to nuclear density, approximately 10^13 grams per cubic centimeter, To put this in perspective, a sugar cube-sized piece of this material would weigh as much as all of humanity combined. At these densities, the distinction between individual nuclei disappears entirely, creating a continuous nuclear fluid where quantum effects dominate. Perhaps most fascinating is the phenomenon of superfluidity, which is predicted to occur in pulsar interiors. At temperatures of around 1 billion degrees Kelvin, which is actually cold for these objects, the neutron fluid is expected to form a superfluid state, a quantum state of matter characterized by zero viscosity and the ability to flow without energy loss. This superfluidity has profound implications for pulsar behavior, potentially explaining phenomena like pulsar glitches, where the star's rotation rate suddenly increases. The nuclear matter in pulsars also exhibits other exotic properties. The extreme conditions can lead to the formation of exotic particles such as hyperons, and there's even speculation about the existence of quark matter in the cores of the most massive pulsars. These conditions create a unique laboratory for testing theories about the strong nuclear force and quantum chromodynamics. The interplay between these various states and processes creates a layered structure within the pulsar. From the outer atmosphere through the crust and into the core, each layer represents a different regime of physics, with its own unique properties and behaviors. This structure is crucial for understanding pulsar phenomena, from their cooling rates to their electromagnetic emissions. Understanding nuclear matter in pulsars isn't just an academic exercise, it's crucial for testing our theories about fundamental physics. These objects represent the only places in the universe where we can study matter under such extreme conditions, making them invaluable natural laboratories for physics beyond our terrestrial capabilities. Every new observation of pulsar behavior provides another piece of the puzzle in our understanding of matter at its most fundamental level. The magnetic fields of pulsars are among the most powerful in the known universe, representing a realm of electromagnetism far beyond anything we can create on Earth. These fields, which can be trillions of times stronger than Earth's magnetic field, play a crucial role in making pulsars the cosmic lighthouses we observe. The extraordinary strength of pulsar magnetic fields originates from the principle of magnetic flux conservation during stellar collapse. When a massive star implodes to form a pulsar, its magnetic field lines are compressed into a much smaller volume. Think of it like this. If you had a piece of paper with drawn lines representing magnetic field lines, and you crumpled that paper into a tiny ball, the lines would become much more densely packed. The same principle applies during stellar collapse, but on a cosmic scale. As the star's surface area decreases by a factor of around 100 billion, the magnetic field strength increases proportionally, resulting in surface fields typically around 10 to a 12 Gauss, compared to Earth's modest 0.5 Gauss. The intensification of these magnetic fields creates conditions that challenge our understanding of physics. At such extreme strengths, the magnetic fields can actually distort atomic structures and create peculiar quantum effects. The magnetic field becomes so strong that it can affect the behavior of light itself, causing it to split into two components with different polarizations, a phenomenon known as vacuum birefringence. The magnetosphere of a pulsar is perhaps one of the most fascinating structures in astrophysics. It extends far beyond the pulsar's surface and is filled with charged particles that are forced to follow the rotating magnetic field lines. This creates a complex and dynamic environment where particles are accelerated to nearly the speed of light. The magnetosphere is divided into distinct regions, including the closed field line region where particles are trapped, and the open field line regions near the magnetic poles where particles can escape, creating the characteristic beams of radiation we observe. The magnetic field lines form a precise and intricate geometry that determines much of a pulsar's observable behavior. Near the pulsar's surface, these field lines are so strong they can actually tear particles from the crust. As they extend outward, they form a distinctive pattern similar to Earth's magnetic field, but far more intense. At a certain distance from the pulsar, known as the light cylinder, the co-rotation speed would exceed the speed of light, leading to a complex interaction between the magnetic field and the surrounding space. One of the most remarkable features of pulsar magnetic fields is their role in particle acceleration. In the strong field regions near the magnetic poles, electrons and positrons are accelerated to relativistic speeds, producing the intense beams of radiation we observe as pulses. These particles follow curved paths along the magnetic field lines, generating synchrotron radiation across a broad spectrum from radio waves to X-rays. The interaction between the pulsar's rotation and its magnetic field also creates an enormous electric field, strong enough to pull charged particles from the pulsar's surface. This process, known as electron-positron pair creation, fills the magnetosphere with a plasma that plays a crucial role in generating the pulsar's emission. Over time, these powerful magnetic fields gradually decay, converting their energy into radiation and particle acceleration. This decay influences the pulsar's long-term evolution and eventually leads to changes in its rotational period and emission characteristics. If you're amazed by this extreme physics, you might be wondering what other objects in the universe could exhibit such extraordinary conditions. Perhaps you could share your thoughts. Could black holes, quasars, or even the mysterious dark matter possess properties that are equally extreme? Leave your like and let us know in the comments what other cosmic objects you think might challenge our understanding of physics in such fundamental ways. Understanding pulsar magnetic fields isn't just about studying these remarkable objects. It's about pushing the boundaries of our knowledge of electromagnetism, quantum mechanics, and the fundamental forces that shape our universe. Each new discovery about pulsar magnetism brings us closer to understanding how matter behaves under the most extreme conditions nature can provide. The emission mechanism of pulsars represents one of the most sophisticated natural particle accelerators in the universe, creating an extraordinary process that generates their characteristic lighthouse-like beams. These emissions are the result of several complex physical processes working in concert, producing radiation that can be detected across vast cosmic distances. Synchrotron radiation lies at the heart of pulsar emission. This process occurs when charged particles, primarily electrons and positrons, are accelerated in curved paths along magnetic field lines. As these particles spiral around the magnetic field lines, they emit electromagnetic radiation in a broad spectrum, from radio waves to X-rays. What makes this particularly fascinating is the relativistic nature of the particles. They're moving at speeds approaching the speed of light, which causes their radiation to be highly focused in the direction of motion, like a cosmic searchlight. Particle acceleration in pulsars occurs through several mechanisms. The primary acceleration takes place in regions called gaps, areas in the pulsar's magnetosphere where powerful electric fields exist. These gaps can be found near the pulsar's surface, polar cap region, or in the outer magnetosphere, outer gap region. Within these gaps, particles are accelerated to relativistic energies by electric fields so strong they can rip particles directly from the pulsar's surface. These particles then cascade into pairs of electrons and positrons, creating an avalanche effect that produces the dense plasma responsible for the pulsar's emission. The radiation beams emitted by pulsars are highly collimated streams of electromagnetic energy. These beams are not continuous, but structured, with complex patterns that depend on the configuration of the pulsar's magnetic field and the distribution of accelerated particles. The emission is typically concentrated in narrow beams that sweep across space like cosmic lighthouses. What we observe as pulses are actually these beams crossing our line of sight as the pulsar rotates. The emission cone represents the geometric pattern of radiation around the pulsar's magnetic axis. This cone isn't uniform, but often shows complex substructures, including core and conal components. The shape and structure of this emission cone can vary significantly between different pulsars and even change with observing frequency. Some pulsars show multiple emission components, suggesting a nested cone structure or the presence of additional emission regions. An intriguing aspect of pulsar emission is its coherent nature, particularly at radio wavelengths. This means the radiation from many particles is somehow synchronized, producing emission far more intense than would be possible from individual particles radiating independently. This coherent emission process is still not fully understood and remains an active area of research in pulsar physics. The emission mechanism also exhibits fascinating temporal behavior. Besides the regular pulses, many pulsars show phenomena such as microstructure, incredibly brief intensity variations within individual pulses, nulling, where the pulsar temporarily stops emitting, and mode changing, where the pulse profile suddenly switches between two or more stable configurations. Temperature plays a crucial role in pulsar emission as well. The surface temperature of a typical pulsar is around 1,000,000 degrees Kelvin, but this thermal emission is often overshadowed by the non-thermal radiation from accelerated particles. The combination of thermal and non-thermal processes creates a complex spectral energy distribution that can provide valuable information about conditions near the pulsar surface. The efficiency of pulsar emission mechanisms is remarkable. Despite the enormous energy involved, pulsars can maintain steady emission for millions of years, gradually slowing their rotation as they convert rotational energy into electromagnetic radiation. This process, known as spin-down, provides crucial insights into the pulsar's age and energy budget. Understanding pulsar emission mechanisms has implications far beyond astronomy. These natural particle accelerators achieve energies far beyond what we can create in terrestrial laboratories, making them invaluable laboratories for testing theories of high-energy physics and electromagnetic processes under extreme conditions. Each advance in our understanding of pulsar emission brings us closer to unraveling the fundamental physics that governs these extraordinary cosmic lighthouses. The interaction between the emission mechanism and the surrounding environment can also create additional phenomena, such as pulsar wind nebulae, glowing clouds of particles and radiation that surround some pulsars. These nebulae provide additional evidence of the powerful particle acceleration processes at work and offer another window into the physics of these remarkable objects. Pulsars serve as cosmic laboratories where quantum mechanics manifests on a macroscopic scale, creating phenomena that exist nowhere else in the observable universe. These extraordinary objects showcase quantum effects not just at the microscopic level, but across their entire structure, making them unique testing grounds for fundamental physics. Superconductivity in pulsars exists under conditions far more extreme than any terrestrial environment. Within the pulsar's crust, electrons form what's known as a relativistic superconductor, where electrical resistance virtually disappears. This state occurs because the intense pressure and magnetic fields force electrons into highly ordered quantum states. Unlike laboratory superconductors that require extremely low temperatures, pulsar superconductivity persists at temperatures of millions of degrees due to the extreme density and pressure conditions. This superconducting state plays a crucial role in the pulsar's magnetic field evolution and thermal properties. Superfluidity represents another fascinating quantum state within pulsars. The neutron-rich interior is believed to form a superfluid, where particle movement occurs without friction. This quantum state arises when neutrons pair up in a manner similar to electrons in superconductors, following what physicists call BCS theory, named after Bardeen, Cooper, and Schrieffer. The superfluid state has profound implications for pulsar behavior, particularly in explaining phenomena like pulsar glitches, sudden changes in rotation speed that provide evidence for the superfluid's existence. Relativistic effects in pulsars create an intricate interplay between quantum mechanics and Einstein's theory of relativity. The extreme gravitational fields cause significant time dilation, meaning time actually flows differently at different depths within the pulsar. This affects quantum processes throughout the star and creates unique conditions where both quantum mechanics and general relativity must be considered simultaneously. The rapid rotation of pulsars also introduces frame-dragging effects, where space-time itself is dragged along with the rotating star, affecting quantum states and particle behavior. The equation of state for pulsar matter represents one of the most challenging problems in modern physics. This mathematical description must account for how matter behaves under conditions where quantum effects, strong nuclear forces, and extreme gravity all interact. The equation must describe how pressure relates to density in a regime where traditional physics breaks down. Different theoretical models predict different equations of state, and observations of pulsar properties help constrain which models might be correct. Among the most fascinating quantum phenomena in pulsars is the possible existence of exotic states of matter. In the densest regions, quarks might become deconfined, creating what physicists call quark matter or strange matter. This would represent a fundamentally different state of matter, where the basic building blocks of neutrons and protons exist in a free state. Some theories even suggest the existence of color superconductivity, where quarks form Cooper pairs in a manner analogous to electrons in conventional superconductors. The quantum vacuum around pulsars also exhibits extraordinary properties. The intense magnetic fields are strong enough to create virtual particle-antiparticle pairs from the vacuum, a quantum effect predicted by QED. These fields can even cause vacuum birefringence, where the quantum vacuum becomes anisotropic and affects the propagation of light in different directions. Temperature effects in pulsars create unique quantum scenarios. Despite their incredibly high temperatures, quantum effects dominate because of the extreme densities involved. This creates a situation where both thermal and quantum effects must be considered simultaneously, leading to unique phases of matter not seen anywhere else in nature. Quantum entanglement, typically observed only at microscopic scales, might play a role in pulsar physics at macroscopic levels. The highly ordered states of matter in pulsars could maintain quantum correlations across relatively large distances, though observing such effects directly remains a significant challenge. Understanding these quantum phenomena in pulsars is crucial not just for astrophysics, but for fundamental physics as well. Pulsars provide natural experiments testing quantum mechanics under conditions impossible to recreate on Earth, helping us verify and refine our theories about how matter behaves under extreme conditions. Each new observation of pulsar behavior provides another piece of evidence in our quest to understand the quantum nature of the universe at its most fundamental level. Let's begin with the most magnetic pulsar ever discovered, a class of objects known as magnetars. The current record holder is SGR 180620, with a surface magnetic field estimated at a staggering 2.4 times 10 to the power of 15 Gauss. To put this incomprehensible number in perspective, this magnetic field is so powerful that it could erase a credit card's magnetic strip from a distance of about 200,000 kilometers, roughly half the distance to the Moon. If this magnetar were as close to Earth as the Moon, its magnetic field would be strong enough to disrupt the atomic bonds holding molecules together in our bodies. Surface temperatures of pulsars reveal another fascinating extreme of nature. Newly formed pulsars typically have surface temperatures around 600,000 to 2 million Kelvin. Despite these incredible temperatures, they cool relatively quickly by astronomical standards. For comparison, our Sun's surface temperature is just 5,778 Kelvin. What's particularly interesting is how pulsars cool unevenly. Their magnetic poles are often significantly hotter than their equatorial regions, creating temperature variations that can exceed hundreds of thousands of degrees across their surface. When it comes to rotation speeds, PSR J17482446AD holds the current record as the fastest spinning pulsar known to humanity. This cosmic speedster rotates an astounding 716 times per second. That means its surface is moving at approximately 24% the speed of light. At such speeds, if this pulsar were just slightly larger or rotated just slightly faster, it would literally tear itself apart due to centrifugal forces. For comparison, consider that while Earth takes 24 hours to complete one rotation, this pulsar completes more than 2.5 million rotations in the same time period. Pulsar glitches represent one of the most mysterious phenomena in pulsar behavior. These are sudden increases in rotation speed, where a pulsar's spin rate abruptly increases by a tiny fraction, typically 1 part in a million. The Vela pulsar is particularly famous for its glitches, experiencing one roughly every 3 years. These events are believed to be caused by starquakes or by the sudden transfer of angular momentum from the pulsar's superfluid interior to its solid crust. Think of it like a tiny cosmic hiccup that makes the entire star briefly spin faster. The double pulsar system, PSR J07373039, where two pulsars orbit each other, provides one of the most stringent tests of Einstein's theory of general relativity. The precision of their orbital measurements is so extreme that they've confirmed Einstein's predictions to within 0.05%. The first pulsar, discovered by Jocelyn Bell Burnell in 1967, was initially nicknamed LGM-1, Little Green Men, because its regular pulses were so precise that scientists briefly considered it might be a signal from an alien civilization. The densest known pulsars pack the mass of about 500,000 Earths into a sphere roughly the size of Manhattan. A single sugar cube of this material would weigh as much as all human beings combined. Some pulsars experience mode changing, where they switch between two or more distinct patterns of pulsation. It's as if they have multiple personalities, each with its own unique rhythm of emission. The phenomenon of nulling, where pulsars temporarily stop their regular pulsations, remains one of the most puzzling aspects of pulsar behavior. Some pulsars can go silent for seconds to hours before resuming their regular beats, and scientists still debate the exact mechanism behind this behavior. The precision of pulsar timing is so exceptional that variations of less than a microsecond can be detected. This makes them more accurate timekeepers than the best atomic clocks on Earth over long periods, leading to their use in pulsar timing arrays for detecting gravitational waves. These extraordinary characteristics of pulsars continue to challenge our understanding of physics and provide natural laboratories for testing theories under conditions impossible to recreate on Earth. Each new discovery about these fascinating objects brings us closer to understanding the fundamental laws that govern our universe. The internal structure of pulsars remains one of the most debated topics in astrophysics. Dr. Victoria Caspi from McGill University, a leading expert in pulsar physics, suggests that understanding the internal composition is crucial for solving fundamental physics questions. Some theorists, like Dr. Mark Alford from Washington University, propose that the core might contain exotic quark matter in a state called a color superconductor. However, others, including Dr. James Latimer from Stony Brook University, argue for a more conventional neutron-dominated core structure. The emission mechanism debate is particularly active in the scientific community. Dr. Alice Harding from NASA's Goddard Space Flight Center has developed models suggesting that pulsar emissions originate from particle acceleration in the outer magnetosphere. In contrast, Dr. Jonathan Ahrens from UC Berkeley advocates for models focusing on acceleration zones near the pulsar's surface. Recent observations from the Chandra X-ray Observatory have provided evidence supporting aspects of both theories, suggesting that multiple emission mechanisms might operate simultaneously. The composition debate extends to questions about the exotic states of matter within pulsars. Dr. Danny Page from the National Autonomous University of Mexico argues for the presence of hyperons, particles containing strange quarks, in the densest regions. However, Dr. Paweł Heinzel from the Polish Academy of Sciences presents compelling evidence for a purely nucleonic composition. This debate has significant implications for our understanding of fundamental particle physics. Current research directions are diverse and exciting. Teams at major facilities like the Very Large Array are conducting unprecedented surveys of pulsar populations. The NICER instrument on the International Space Station is making precise measurements of pulsar radii, helping constrain equations of state. International collaborations are using pulsar timing arrays to detect gravitational waves, potentially opening a new window into cosmic phenomena. Let's pause for a moment and consider this mind-bending scenario. What would happen if we could transport a single cubic centimeter of pulsar matter to Earth? The consequences would be nothing short of catastrophic. This tiny cube, about the size of a sugar cube, would weigh approximately 100 million tons, equivalent to the weight of all human-made structures in New York City. The moment it materialized on Earth, several extraordinary things would happen simultaneously. First, its immense gravitational field would immediately begin pulling everything nearby towards it. Cars, buildings, and even people within several kilometers would be drawn toward this incredibly dense object. Second, the sudden release from the pulsar's intense pressure would cause the neutron matter to explosively decompose. The neutrons would quickly decay into protons and electrons, releasing an enormous amount of energy, essentially creating a miniature nuclear explosion. Third, the intense magnetic field contained within this small cube would disrupt electronic devices for kilometers around and could potentially be strong enough to affect the molecular bonds of nearby matter. The combination of these effects would create an event similar to a small nuclear detonation, leaving a substantial crater and causing widespread damage. Fortunately, such a scenario remains purely theoretical. The laws of physics make it impossible to transport such matter intact across space. This thought experiment illustrates just how extreme the conditions inside a pulsar truly are, and why these objects are so valuable for testing our theories about matter under extreme conditions. What other cosmic objects do you think could have similarly extreme properties? Take a moment to consider and share your thoughts in the comments. By presenting these expert perspectives and engaging thought experiments, we not only understand the current state of pulsar research, but also appreciate the incredible nature of these cosmic objects and their importance in modern astrophysics. Advanced physics plays a crucial role in understanding pulsars, and we can break down these complex concepts into more digestible pieces. Let's explore how different branches of physics come together to explain these fascinating cosmic objects. Special relativity, Einstein's groundbreaking theory, is fundamental to pulsar physics. When we observe pulsars, we're watching objects that demonstrate relativistic effects in action. Their rapid rotation causes the outer regions to move at significant fractions of the speed of light. This leads to time dilation effects, where time actually moves more slowly in these rapidly moving regions compared to the pulsar's core. The famous equation EMC2 becomes particularly relevant when we consider the enormous energies involved in pulsar emissions and the conversion of mass to energy in their formation process. The particles ejected from pulsars often travel at speeds approaching the speed of light, requiring relativistic calculations to understand their behavior. This involves phenomena like relativistic beaming, where the radiation is concentrated in a narrow cone in the direction of motion, making pulsars appear brighter when their beams point toward Earth. The concept of relativistic mass increase also becomes important, as particles gain effective mass as they approach light speed in the pulsar's powerful accelerating fields. Electromagnetism in pulsars showcases nature's most powerful magnetic fields. These fields, typically trillion times stronger than Earth's, create conditions where classical electromagnetic theory meets quantum effects. The magnetic fields are so intense that they can actually distort the quantum vacuum, creating virtual particle-antiparticle pairs from empty space. The rotating magnetic field generates enormous electric fields through electromagnetic induction, accelerating particles to relativistic speeds and creating the characteristic pulsar beams we observe. The interaction between the magnetic field and charged particles produces various types of electromagnetic radiation, from radio waves to gamma rays. This radiation is often highly polarized due to the ordered nature of the magnetic field, providing astronomers with valuable information about the pulsar's structure. The complex interplay between the rotating magnetic field and the surrounding plasma creates a magnetosphere with distinct regions where different electromagnetic processes dominate. Quantum mechanics becomes essential when describing matter under pulsar conditions. The extreme densities in pulsars force electrons into quantum states where the Pauli exclusion principle plays a crucial role. This quantum mechanical principle prevents matter from collapsing further under gravity by creating a degeneracy pressure. The quantum nature of matter becomes evident in phenomena like superfluidity, where particles form coherent quantum states extending over macroscopic distances. The quantum tunneling effect allows particles to escape from the pulsar's surface in ways that classical physics cannot explain. Moreover, quantum effects determine how radiation is produced and absorbed in the pulsar's atmosphere, leading to unique spectral signatures. The quantum nature of the electromagnetic field itself becomes important in understanding how radiation propagates through the intense magnetic fields surrounding pulsars. Nuclear physics governs the very heart of pulsars. During their formation, atomic nuclei are crushed together under enormous gravitational pressure, forcing electrons to combine with protons to form neutrons through inverse beta decay. The resulting neutron-rich matter exists in a state that can only be understood through nuclear physics. The strong nuclear force becomes the dominant interaction holding this matter together, creating an environment where nuclear physics operates on a stellar scale. The nuclear equation of state, which describes how matter behaves under these extreme conditions, remains an active area of research. Some theories suggest that at the core of the most massive pulsars, even neutrons might break down into their constituent quarks, creating a state of matter called quark matter. This would represent a phase transition where nuclear physics gives way to even more fundamental particle physics. Understanding these four branches of physics and their interplay is crucial for explaining pulsar behavior. From the relativistic effects of their rapid rotation to the quantum and nuclear processes in their cores, pulsars serve as natural laboratories where multiple branches of physics converge. These cosmic objects continue to challenge our understanding and push the boundaries of physics, making them invaluable tools for testing our most fundamental theories about the universe. The study of pulsars has led to some of the most dramatic revelations in modern astronomy, fundamentally changing our understanding of the universe. Let's explore these breakthrough discoveries that have transformed theoretical physics into observable reality. The connection between pulsars and gravitational waves represents one of the most exciting frontiers in modern astronomy. Pulsars serve as precise cosmic timekeepers, creating a natural array of detectors for gravitational waves. Scientists are currently using pulsar timing arrays, monitoring dozens of millisecond pulses across the galaxy to detect the subtle ripples in spacetime caused by supermassive black hole mergers. These arrays act like a cosmic web of detectors, with each pulsar's regular signals being subtly disturbed by passing gravitational waves. Recent observations have revealed tantalizing evidence of a background hum of gravitational waves permeating the universe. This discovery, announced in 2023, suggests that we're detecting the collective effect of countless supermassive black hole mergers throughout cosmic history. The precision of pulsar timing is so extraordinary that we can detect variations in their signals down to nanoseconds, allowing us to measure distortions in space-time smaller than an atomic nucleus. Pulsars have played a pivotal role in verifying Einstein's theory of general relativity. The discovery of the binary pulsar PSR B191-16 by Russell Hulse and Joseph Taylor provided the first indirect evidence of gravitational waves, earning them the 1993 Nobel Prize. This system showed exactly the orbital decay predicted by Einstein's theories, as it lost energy through gravitational wave emission. More recently, the double pulsar system PSR J07373039 has provided even more stringent tests, confirming general relativity's predictions to within 0.05% accuracy. The extreme conditions around pulsars create natural laboratories for testing gravity in ways impossible on Earth. We've observed phenomena like gravitational lensing, frame dragging, and the geodetic effect, all precisely matching Einstein's predictions. The recent discovery of a triple star system containing a pulsar has opened new opportunities to test theories of gravity under even more complex conditions. Discoveries about pulsars' internal structure have been equally revolutionary. Advanced X-ray observatories like NASA's NICA mission have made breakthrough measurements of pulsar radii and masses, providing unprecedented insights into their internal composition. These observations have helped resolve long-standing debates about the equation of state of ultra-dense matter, suggesting that neutron star cores might be less exotic than some theories predicted. Perhaps most surprisingly, recent evidence suggests that some pulsars maintain a thin atmosphere of plasma despite their enormous surface gravity. This discovery helps explain various emission phenomena and challenges our previous models of pulsar surface conditions. We've also found evidence of mountains on pulsar surfaces, tiny irregularities just centimeters high that nonetheless contain more mass than Mount Everest due to the extreme density. The latest data from radio telescopes has revealed complex structures in pulsar magnetospheres, showing they're far more dynamic than previously thought. We've observed sudden changes in magnetic field configurations, suggesting that pulsars undergo dramatic magnetic reconnection events similar to solar flares, but millions of times more powerful. One of the most startling recent discoveries involves pulsar glitches, sudden increases in rotation speed. New observations suggest these events might be linked to superfluid behavior in the pulsar's interior, where quantum effects operate on a stellar scale. This provides direct evidence of quantum phenomena occurring at macroscopic levels, bridging the gap between quantum and classical physics. The role of pulsars in understanding the evolution of the universe has also expanded dramatically. By studying pulsar distributions and properties, we're gaining new insights into stellar evolution, galaxy formation, and even the distribution of dark matter in our galaxy. The recent discovery of pulsars near the galactic center is providing unique tools for testing gravity in the presence of our galaxy's supermassive black hole. Looking forward, plans for next-generation radio telescopes promise even more revelations. The square-kilometer array, when completed, will likely discover tens of thousands of new pulsars, potentially including the Holy Grail, a pulsar, orbiting a black hole. Such a system would provide unprecedented tests of gravity in the strongest possible gravitational fields. These discoveries highlight how pulsars continue to surprise us, challenging our understanding of physics and revealing new mysteries even as they help solve old ones. Each new finding opens up new questions, driving forward our exploration of the universe's most extreme objects and the fundamental laws that govern them. The study of pulsars extends far beyond pure scientific curiosity, profoundly impacting our technological capabilities, fundamental understanding of physics, and grasp of extreme matter states. These cosmic lighthouses have become deeply intertwined with human technological advancement and our quest to understand the universe. The precision timing of pulsars has led to remarkable technological applications. Scientists have developed pulsar-based navigation systems that could revolutionize space travel. Similar to how ancient mariners used celestial navigation, spacecraft can use pulsars as cosmic GPS satellites. NASA's NICER experiment on the International Space Station is already demonstrating this technology's potential. This pulsar-based navigation could provide autonomous spacecraft guidance throughout the solar system, enabling more reliable deep space exploration. Pulsar timing has also contributed to the development of ultra-precise atomic clocks. The regular pulses from millisecond pulsars are so consistent that they rival our best atomic timekeepers. This has pushed engineers to develop even more accurate timing systems, benefiting everything from global positioning systems to financial trading networks. The extreme precision required to measure pulsar signals has driven advances in radio telescope technology and signal processing techniques, with applications extending to everyday telecommunications and data analysis. In fundamental physics, pulsars serve as natural laboratories for testing theories that would be impossible to verify on Earth. They have provided some of the strongest evidence for Einstein's theory of general relativity. The famous Hulse-Taylor binary pulsar system demonstrated the existence of gravitational waves decades before we could detect them directly, earning its discoverers the Nobel Prize. Current pulsar timing arrays are helping scientists detect gravitational waves from supermassive black hole mergers, opening new windows into the universe's most energetic events. The extreme conditions within pulsars have advanced our understanding of nuclear physics. Studying pulsar matter has helped scientists develop better models of atomic nuclei and nuclear forces. This knowledge has practical applications in nuclear physics research facilities and has improved our understanding of nuclear fusion, potentially benefiting future energy technologies. The insights gained from pulsar magnetic fields have enhanced our understanding of plasma physics, contributing to research in nuclear fusion reactors and plasma-based technologies. Perhaps most fascinating is how pulsars have expanded our comprehension of extreme matter states. The matter inside pulsars exists in conditions impossible to recreate in any laboratory on Earth. Understanding how matter behaves under such extreme pressures and densities has implications for materials science and high-pressure physics. This knowledge influences the development of new materials and our understanding of matter under extreme conditions, with potential applications in everything from industrial processes to advanced materials design. The study of pulsars has also contributed to advancements in computational physics. The complex models required to understand pulsar behavior have driven the development of sophisticated computer simulations and numerical methods. These computational techniques have found applications in other fields, from weather prediction to financial modeling. Pulsar research has influenced medical imaging technology as well. The techniques developed to process and analyze pulsar signals have contributed to improvements in medical imaging systems, particularly in processing weak signals from complex backgrounds. Similar signal processing methods are now used in MRI machines and other diagnostic tools. The investigation of pulsar phenomena has even impacted quantum computing research. The quantum effects observed in pulsar matter have provided insights into quantum mechanics at macroscopic scales, contributing to our understanding of quantum systems and their potential applications in quantum computing technologies. The human context of pulsar physics extends to inspiration and education as well. These remarkable objects have captured public imagination and served as gateways to understanding complex physics concepts. They demonstrate how pure scientific research can lead to unexpected practical applications and technological innovations that benefit society. As we continue to study these fascinating objects, new applications and insights emerge. Each discovery about pulsars not only advances our scientific understanding, but also opens new possibilities for technological innovation and practical applications that impact our daily lives. The story of pulsar physics is a testament to how exploring the most extreme objects in our universe can lead to advances that benefit humanity in countless ways. As we conclude our journey through the fascinating world of pulsar physics, we find ourselves at the frontier of human knowledge, where these remarkable cosmic objects continue to challenge and expand our understanding of the universe. Pulsars are indeed far more than mere cosmic lighthouses. They represent nature's most extreme laboratories, pushing the boundaries of physics to their absolute limits. These extraordinary objects embody the convergence of multiple physics disciplines: quantum mechanics, general relativity, nuclear physics, and electromagnetism, all interplay in ways we're still working to fully comprehend. Each pulsar observation provides us with data that would be impossible to obtain in any terrestrial laboratory, offering insights into matter and energy under the most extreme conditions imaginable. The story of pulsars is also a testament to human ingenuity and scientific progress. From their serendipitous discovery by Jocelyn Bell Burnell to their current role in detecting gravitational waves, pulsars have consistently opened new windows into the cosmos. They've helped confirm Einstein's theories, revealed the existence of exotic states of matter, and continue to serve as precise cosmic clocks for testing our fundamental understanding of space and time. Looking ahead, pulsars promise even more discoveries. As our detection methods improve and our theoretical understanding deepens, these cosmic laboratories will undoubtedly reveal new mysteries and potentially revolutionary insights into the nature of matter, energy, and the universe itself. They remain at the forefront of astronomical research, driving innovation in technology and pushing the boundaries of human knowledge. The study of pulsars reminds us that the universe is far more extraordinary than we could have imagined, and that there's still so much to learn. These rotating neutron stars, with their clock-like precision and extreme physics, continue to inspire new generations of scientists and challenge our most sophisticated theories about how the universe works. But this isn't just a story about distant stars. It's a story about human curiosity, ingenuity, and our relentless pursuit of understanding. Every pulsar observation, every theoretical breakthrough, and every new discovery brings us closer to unraveling the fundamental mysteries of our cosmic existence. Before we end this exploration, I want to personally invite you to continue this fascinating journey of discovery with us. Your engagement with complex scientific concepts like pulsar physics shows your curiosity about the universe, and we want to nurture that curiosity. Join our community of cosmic explorers at Exploring the Universe by subscribing to our channel. By activating the notification bell, you'll ensure you never miss our latest videos about the wonders of astronomy and physics. Each like, share, and comment helps us reach more curious minds like yours, spreading the excitement of scientific discovery. Together, we can continue to explore the mysteries of pulsars and countless other fascinating astronomical phenomena. Share this video with friends who might be intrigued by the extreme physics of pulsars, and let's build a community dedicated to understanding the cosmos. Thank you for joining me on this journey through the physics of pulsars. Don't forget to hit that subscribe button, activate notifications by clicking the bell icon, and leave a like if you enjoyed this exploration. Share this video with fellow science enthusiasts, and let's keep exploring the universe together. Until our next cosmic adventure, keep looking up and wondering about the extraordinary physics that shapes our universe. This is Exploring the Universe, where every video brings us closer to understanding the cosmic mysteries that surround us.